Welcome back. In this video, we will be discussing atomic theory and the history of the atom. Let's begin with the concept of atomic theory. The ancient Greeks originally developed the concept of an atom as a particle that cannot be divided, the building block of all matter. Their word, atomos, remains the root of the word atom today. The modern view of atoms was theorized by John Dalton around 200 years ago. He had several claims. First, that each element is made of tiny particles called atoms. Second, the atoms of each element are identical to each other, but somehow different from the atoms of other elements. Third, the chemical compounds are formed by atoms of different elements coming together in a fixed ratio. Finally, he said that chemical reactions involve the reorganization of atoms moving from one compound to another. Where did all of these ideas come from? Well, in addition to the early ideas of the Greeks, Dalton used the work of many contemporary scientists in order to fully develop his theory. Antoine Lavoisier is credited with the experimental verification of the law of conservation of mass, which states that mass is neither created nor destroyed in a chemical reaction. Joseph Proust is credited with the determination of the law of definite proportion, which states that a given compound always contains exactly the same ratio of elements by mass. Finally, Dalton himself determined the law of multiple proportions. Now, this states that whenever two elements form a series of compounds, the ratios of the masses of the second element that combine with exactly 1 gram of the first element can always be reduced to small whole numbers. Okay, how does that work? Well, let's do an example. We know that there are several compounds that can be made out of just nitrogen and oxygen. We'll call one of them compound A. Now, compound A can be made from 1.750 grams of nitrogen along with exactly 1 gram of oxygen. Next, we have compound B. Now, compound B is made from 0.875 grams of nitrogen, again, along with exactly 1 gram of oxygen. Finally, a third compound, we'll call it C. And compound C is made from 0.4375 grams of nitrogen. Again, exactly 1 gram of oxygen as well. Now, what the law of multiple proportions states is that we can compare the ratio of the masses of nitrogen. So, the ratio of compound A to compound B is just going to be 1.750 grams over 0.875 grams. And this ratio simplifies to 2 to 1. We'll do the same thing and look at the ratio of B to C. In this case, 0.875 grams for compound B is divided by 0.4375 grams of compound C. This ratio is also exactly 2 to 1. One final, we can compare compounds A and C. The ratio of compound A over compound C, well, this must be 1.750 grams over 0.4375 grams. And this is a ratio of 4 to 1. This lets us see that all three compounds have a simple ratio of nitrogen atoms to oxygen atoms, and that these ratios of elements must be what make the compounds different from each other. Now that our atomic theory has been established and the concept of an atom starts to make some sense, scientists began to wonder exactly how the atoms of different elements are different from each other. The first major discovery of atomic structure came in the beginning of the 1900s when J.J. Thomson performed a series of experiments with cathode ray tubes. Now, these are glass tubes emptied of air and having electrodes placed on either end. When plugged into an electrical source, this produces a stream of particles from the negatively charged electrode. Now, since the negatively charged electrode is called a cathode, that's where we come up with the name cathode ray tube. These negatively charged particles were named electrons. While Thomson couldn't directly determine the charge or the mass of the electrons, he was able to figure out the charge to mass ratio. He found that 1 gram of electrons, now a lot of times electrons are abbreviated with a lowercase e and a minus charge, indicating that they are negatively charged. And this has a charge of negative 1.76 times 10 to the 8th coulombs, where a coulomb is a unit of electrical charge. Now, since these electrons could come from any cathode, no matter what element was used, Thomson decided that all atoms must include these electrons. Later, in 1909, Robert Millikan cleverly determined the charge of an electron using what he called the oil drop experiment. From this and our charge to mass ratio, he found that the electron has a mass of about 9.11 times 10 to the minus 31 kilograms. A single electron has a very tiny mass. Well, if we know the mass, can we figure out its charge? We'll use the numbers determined by Thomson and Millikan in order to calculate this value. Remember, Millikan determined that the mass of a single electron is 9.11 times 10 to the minus 31 kilograms, and Thomson determined our charge to mass ratio is 1.76 times 10 to the 8th coulombs per gram of electrons. So let's set up our calculation, starting off with that first number, 9.11 times 10 to the negative 31 kilograms per single electron. Now, our other unit conversion has grams in it, so remember that we can convert from 1 kilogram into 10 to the 3 grams. Finally, we'll use Thomson's ratio. We want to make sure to cancel out grams on the bottom, so remember that a single gram of electrons has a charge of negative 1.76 times 10 to the 8th coulombs. Putting all of this into our calculator and making sure to cancel kilograms with kilograms and grams with grams tells us that the charge of a single electron is negative 1.60 times 10 to the minus 19 coulombs per electron. With the work of Thomson and Millikan, we know that all atoms have electrons existing as very small negatively charged particles. Now, Thomson originally thought that the positively charged parts of an atom must surround these negative electrons. But a few years later, in 1911, Ernest Rutherford tested this hypothesis using what we call the gold foil experiment. He expected that a diffuse positively charged atom, like Thomson hypothesized, should have no effect on the alpha radiation he was directing through a thin sheet of gold foil. Instead, he found that while many of the alpha particles passed through the sheet without interruption, a significant number were deflected. Now, these deflections could only be caused by a small, concentrated positive charge containing the vast majority of the atom's mass. This was the first experimental evidence of the atom's nucleus. The charge of the nucleus was quickly identified as the unique factor that distinguishes each element from all the others. Soon thereafter, it was discovered that the amount of charge in the nucleus is determined by the number of positively charged particles, named protons, inside of it. Now, protons will often be abbreviated with a lowercase letter p. These protons, and later found electrically neutral particles called neutrons, given as an N, are known to make up the nucleus of all atoms. Thus, our modern view of the atom, consisting of a dense positively charged nucleus containing protons and neutrons, as well as a few very spread out negatively charged electrons, was born. In order to get an idea of the scale of an atom, if we had an atom the size of Kyle Field, the nucleus would really only be about as large as an M&M.